I'm on YouTube.
Alright. So first off, we're talking about the segments that can be drawn into a triangle. We have a median of a triangle. A median is a segment that can be drawn from a vertex to the midpoint of the opposite side. So in a triangle, you could have any triangle. You could draw the median from any vertex to any of the sides. So if I find the midpoint of this side, then the segment that goes from this vertex to that midpoint is one of the medians that can be drawn in the triangle. You could picture then that we could actually have many triangles. Sorry, many medians drawn in one triangle, and I was just surprised at what it did there. It helped what I did not realize I was in Geometry Sketchpad, but I am. Okay. So let's go ahead and draw a triangle and draw the three medians in this triangle. So I'm going to construct segments to make a triangle. Define the midpoint of one side, and then draw a segment connecting those 2 points, and that is the median. You don't have to. What we're going to do now is play with this a little bit and take a look at what it looks like when we draw all three medians in the triangle. So now if I draw a median to this side,
No.
yes, Angelica.
I was just saying to start.
Okay, go ahead.
The corner by the side.
So I would go from this vertex to that side, wouldn't I? Yes. So let's go ahead and construct a midpoint. And then let's go ahead and draw a segment if I can get those points selected. What do you think is going to happen when I draw this third median? If I connect the midpoint with this opposite vertex, you end up with a midpoint inside the triangle, don't you? This point right here is in fact called the centroid, which is the center of gravity. If you have a material that is of uniform thickness, and you find this point, then you could balance that triangle on that compass point, basically, at that location. If there's a little resting spot for the compass point, you could actually spin the triangle on the compass point at that location, because it is the center of gravity. It's its balancing point. These thicker lines, I'm going to make them bold now. Those thicker lines are the medians in the triangle, which means that all of these are midpoints of the opposite side. Okay, let's go ahead and capture that picture. Okay. I'm going to make it smaller now. Let's go to the next. So that's a median. The next one we're going to look at is an altitude. An altitude drawn from a vertex perpendicular to the opposite side. Now, if my triangle is obtuse and I want to go from this vertex perpendicular to the opposite side, the altitude will have to go outside the triangle. How do I go perpendicular to this side right here from that vertex? I have to go outside the triangle, don't I? So you have to extend this side if your triangle is obtuse, and then that is an altitude. Altitude is a segment drawn from a vertex perpendicular to the opposite side. We could draw altitude from any of these vertices. So if I wanted an altitude from that vertex, then I would need to go perpendicular to the opposite side. If I wanted the altitude from this vertex, I would have to extend this other side out, wouldn't I? Because I have to be perpendicular to the opposite side. Those would be the three altitudes. What would it look like if we draw three altitudes in Geometry Sketchpad? So here's a triangle. And I want the altitudes, which means I want to be perpendicular to this side from that point. Perpendicular line, there we go. Let's make these lines thin. That's one of the altitudes. Now, if I move the triangle around, you can see that sometimes the altitude is outside the triangle. When the triangle is obtuse, when the triangle is right, the altitude is one of the sides of the triangle. Because the computer kind of sees it. Now, let's draw the other altitudes. So perpendicular from this vertex to the opposite side, and finally perpendicular. No, this point where these intersect is called an orthocenter, and it's not always in the triangle. That point is sometimes outside the triangle. So if I move the triangle around, you can take a look at what is happening.
Awesome. Oh my God.
Sometimes the point
Whoa.
is outside the triangle if the triangle is obtuse. If the triangle is right, then it's on the triangle.
That's cool.
If the triangle is acute, then it's in the triangle. And you can
Whoa.
expand it.
It's only 2 euros.
Okay, that is the altitudes and where they intersect. Sometimes it's inside the triangle. Now, our next line segment, we have perpendicular bisectors. Now, we've talked about perpendicular bisectors before. A perpendicular bisector kind of tells what it does in its name. Perpendicular, 90-degree angle. Bisector, through a midpoint. So the perpendicular bisectors of the sides of a triangle will be perpendicular to this side through its midpoint. segment here. I probably should have said a line or something like that, right? Because it does not have to be a segment. Now,
Look, it says a line, array, or segment.
right, it could be any of those. So if I have a triangle then, and we want to talk about a perpendicular bisector, we need to find a midpoint, and then we need to draw a line perpendicular to that side through its midpoint. Let's ungroup that. So we'll move it over a little bit. Ungroup, move my line so it goes through that midpoint. Will that perpendicular line always go through the opposite vertex? No. When does it go through the opposite vertex? When the triangle is isosceles.
Or equilateral.
Or equilateral. The same thing, yes. So let's go ahead and look at what this might look like if we drew all the perpendicular bisectors. So go into Geometry Sketchpad. Let's get a new sketch. Draw a triangle. And then in order to have a perpendicular bisector, you have to have a midpoint and a perpendicular line. Glancing. So that is a perpendicular bisector right there, this angle. We are looking at probably Wednesday, Thursday, this week. We're almost at the end of the chapter here, so probably Thursday. Now we can see, if you will allow me to change the triangle around, we can see that that line will always be perpendicular to one side of the triangle through its midpoint. And it will go through the opposite vertex only when the triangle is isosceles. Okay? Let's go ahead and look at the other perpendicular bisectors just because we've kind of been exploring this as we go. So I need a midpoint, and I need a perpendicular line. There's another perpendicular bisector. What do you guess about this third perpendicular bisector?
Black magic.
Definitely. What do you guess?
That's a good guess for it.
Then it'll probably go through this point where the other two intersect. Because that's what's been happening, isn't it? So let's go ahead and construct that perpendicular line, and yes, it does. It goes through that exact point. Which means we have another center, don't we? This center is called the circumcenter.
Why doesn't the other line move?
It's because of the side I was moving. Well, you can move a different side then. The reason why that's called a circumcenter is because, actually, if I can find that point, if I would construct a circle with that center going through one of the vertices, what happens to that circle?
It's a very
It's going to go through all three of the vertices, isn't it?
halfway make a pentagram.
We are going to make these lines bold. And then as I move one of these vertices around and change the shape of my triangle, what do you notice about the circle? Yeah, but it's always going to go through
He's the one that sells himself.
the triangle's vertices, isn't it? So that point also has a special purpose to it. Eventually we have compass and straight edge and we're working with that. Okay, on the next one I'll have you guys help me with it. Okay? The last segment we're going to look at is angle bisectors. The angle bisectors of the triangle, each of them will bisect one of the angles of the triangle. So it could be a segment, it could be a line, it could be a ray that bisects an angle of a triangle. bisectors, but not in a triangle. So if I have an angle bisector, it is segment, line, or ray that makes two congruent angles as you draw it from one of the angles of the triangle. Let's go ahead and do this.
Well,
Okay, let's move back so you can get it.
just a second.
How do you do your hair? Like, tied in?
That's good.
At the end of class session now. Okay, so if we look at the angle bisectors, watch closely so you can see as I bisect one of the angles, and then I'll have you guys come up and go ahead and bisect another angle. First off, I have to identify what angle I'm working with by labeling the vertices in the order that I would name the angle. So here I have those three vertices. The one I did in the middle is the angle I will be bisecting, because that's how you name that angle. So when I construct an angle bisector, there you have it. Let's make it be a thin width. Angelica, you want to do the next one? So we're going to bisect another angle. What do you guess about the... Okay, so we're going to bisect this angle, which means I hit the vertices with that one in the middle. And then construct angle bisector. Okay, I'll just do the next one too, because I'm not sure that everyone else is paying attention either. So construct angle bisector. They intersect. Will this point always be in the middle of the triangle? It looks like it. What type of center is this? It's the in-center, meaning it's the center of a circle that can be inscribed or drawn inside this triangle. So what I need is, in fact, a perpendicular construction for the radius. I need the point where those two segments intersect. And then I need a circle with center and radius. And what we have is a circle that is drawn inside the circle, inside the triangle, and in fact will always be tangent to the sides of the triangle. Now, our first theorem we're going to work with, theorem 4-5, deals with the point on the perpendicular bisector of a segment. If a point lies on the perpendicular bisector of a segment, then the point is equidistant from the endpoints of the segment. That lies on the perpendicular bisector. That's what's going to have to be in our diagram. So here's our segment. Locate a midpoint. Draw a perpendicular bisector. And we have a point on that perpendicular bisector. What we want to prove is that it must be equidistant from the endpoints. Now, to talk about that point being equidistant from the endpoints A and B, what we are really meaning is that this segment is equal to that segment. That's what we want to prove. I don't want that in my diagram right now, though. That's what we're going to prove. Our given information is now marked on the diagram, basically. We have this perpendicular bisector to segment AB.
What's the first word that we
Marked on the diagram. What we want to prove is that PA is congruent to PB. But that means point P, since it's on that perpendicular bisector, has to be equidistant from the endpoints. The question is, can I prove these triangles are congruent? Let's label this point M so we can refer to those triangles. Yes, the triangles are congruent by side angle side. Nick and Dustin. So we have triangle PAM is congruent to triangle PBM. Which means PA has to be congruent to PB. Why? Yes. Corresponding parts congruent triangles are congruent. Our next theorem then, theorem 4-6. If a point is equidistant from the endpoints of a segment, then the point lies on the perpendicular bisector of the segment. What we have in this case is we have an isosceles triangle. As we have a point that is equidistant from the endpoints of a segment, and what that looks like, our segment AB, our point P, that is equidistant from the endpoints. That's an isosceles triangle. Now, if I draw the bisector of the vertex angle of this isosceles triangle, we have a theorem about that. The bisector of the vertex angle of an isosceles triangle is perpendicular to the base at its midpoint. That is actually a corollary of the theorem that deals with isosceles triangles. No, theorem 4-1 maybe. If you look at theorem 4-1, you have some corollaries to that theorem. And one of them says the bisector of the vertex angle of an isosceles triangle is perpendicular to the base at its midpoint. Corollary 3 of theorem 4-1. So, first off, let's write what is given and what is to be proved here. We have our given basically marked on the diagram. And what we want to prove. And we'll label this point where the bisector vertex angle goes across AB we'll label that point X. We're going to prove then that PX is a perpendicular bisector of segment AB. And I can do it by corollary 3 of
So you wish you
34.1.
could play basketball this year while we're reading during lunch hour? And if Mrs. Griffith's rule?
So since it's perpendicular to the base at its midpoint, it is a perpendicular bisector. By definition, perpendicular bisector.
Not funny. No, it would be a shame.
Here, 4.7, if a point lies on the bisector of an angle, then the point is equidistant from the sides of the angle. Yep. It says that it perpendicularly bisects segment C. Theorem 4.7. If a point lies on the bisector of an angle, then the point is equidistant from the sides of the angle. Bisector of that angle, and we want to prove that if a point lies on the bisector, that it is equidistant from the sides of the angle. Now here we have angle ABC, but the distance from that point to side AB is not a segment drawn from P to A. In order to go from a distance from a point to a segment, you have to use a perpendicular line. So this distance right here, we'll call that point X, and this distance to the other side, we'll call that point Y. We want to prove that PX is congruent to PY. So our given are the sides as marked. Can we prove these triangles are congruent with the congruent parts that are marked on these triangles? Because that's going to be key to proving that PX is congruent to PY. Congruent parts marked on the diagram.
That's pretty messed up.
probably got it kind of right. I parts mark Don diagram. Okay. What we want to prove is that px is congruent to py. The triangles are congruent by angle, angle, side. Can you see the shared side? So angle, angle, side. Triangle PXB congruent to triangle PYB. And this would mean that PX is congruent to PY. Because corresponding parts of the triangles are congruent. All the rest of these theorems have been kind of quick. Theorem 4.8. Theorem 4.8 says that if a point is equidistant from the sides, then it must lie on the angle bisector. So in this case, what we start out with is a point that is equidistant from the sides. So a point where, if that's x, that px is congruent to, if that's y, py. That's what we start with. And of course we're going to want triangles, so let's draw the line that goes from the vertex, we'll call that vertex A, I guess, through the point P. Do these triangles have to be congruent? It's not side angle side. They do share that side and they have another side, but where's the angle? We can't use side angle, but it's a right triangle, so it's hypotenuse laid. Again, our given is marked on the diagram, and we want to prove that ray AP bisects angle XAY. Kind of. In this case, it wouldn't matter what I called it, because any of them can bisect.
Half an hour earlier.
So if I can show the angle 1's congruent to angle 2, which I can because the triangles are congruent, then this ray bisects angle XAY. And that is basically the Thank you. We might finish tomorrow.